students, welcome to session 3 of Unit 1 in the course Introduction to Abstract Algebra. I am Mukaila Dasan, your course instructor for this course. In the previous section, we described how to combine two mappings to form a single new mapping. In this section, you'll be learning how to find the inverse of a given mapping. That's the session 3 of Unit 1, inverse of a given mapping. By the end of this session, you should be able to state the condition for a mapping to be invertible. That is, we say that the mapping has inverse. Find the inverse if it exists of a given mapping. That is objectives for this section. Inverse mapping. What comes to your mind when you say inverse and then inverse of a mapping? So the inverse mapping can be thinking of something or as a reversal of whatever an original mapping does to its values. So let's take for instance, if I have f of x maps to x plus 1, that is f of x maps to x plus 1. Let's say I want to find the value of 3 when x equals to 3. What do I get? I get 3 plus 1, which equals 4. Now, the inverse mapping here, what it does is that we want to look at the process of reversing the 3 to get back, reversing the 4 to get back the 3. Because you put in 3 to get 4. How do you reverse the process to get the initial condition that was 3? In that instance, you call it inverse of a function, that is f exponent minus 1, that is f prime, and that is f inverse of x. So you can say that f inverse of 4 is actually 3. F inverse of 4 is actually 3. That's the inverse of a function. Good. So let's look at, as I said, that let's look at this theorem and then how it's going to be. So this theorem characterizes the mappings that are invertible, have inverse. When you say a mapping is having inverse, how do you state the theorem? And these are the theorems. The first one, a mapping f of s taking set f to t is invertible if and only if is 1 to 1 and onto. So if your mapping is at the same time 1 to 1 and onto, if your mapping is 1 to 1 and onto, then we say that that mapping is invertible. It might be 1 to 1 at the same time it might be onto. Okay, so theorem 3 is established that a mapping is both 1 to 1 and onto, then it's invertible. Conversely, if it is established that a mapping is invertible, then obviously that mapping is 1 to 1 and onto. That's the opposite. So this theorem, I leave the proof for you. It's not difficult. You find the proof in the other material, that's the course material. Now, let's look at this example 5. Show that the mapping of f moving from a real number to a real number defined by f of x equals x squared is not invertible. I want to show that this mapping has no inverse. It has no inverse. So if we want to show that it's having inverse, then we look for 1 to 1 at the same time onto. So let's check for the 1 to 1 first. Okay, now suppose that f is 1 to 1. Let's suppose that f is 1 to 1. Then we can say that if we let x1 and then x2 all being a member of x, then what do? All be a member of x. Let's say r rather instead of x, because mapping from r to r. If x1 and x2 are all member of the real number r, then one can say that f of x1 must be equal to f of x2, implies that x1 equals to x2. Then we can say that the mapping is 1 to 1. The mapping is 1 to 1. So by this definition, let's test. Let's see f of -1 into the function. What do we get? The same as 1 and the same as f of 1. Because once you put -1 here, you get 1, you put 1 there, you get 1. But here, -1 is actually not equal to 1. Once -1 is not equal to 1, therefore this function is not 1 to 1. Once it fails to be 1 to 1, then the function is not invertible. So not invertible. So therefore f is not invertible because it fails to be 1 to 1 function. Great. Let's see example 16. Example 16 here. We can see that we want to show that the mapping defined by f of x equals x cubed on the set of real numbers is invertible. So how do you show that this function is invertible? Now we show that f is 1 to 1. At the same time, we show that f is onto. Now suppose that, let's say x1, x2 are all members of R. So x1, x2, let's say they all belong to R. Then one can show that if f is 1 to 1, then x1 cube minus x1 cube. Okay, let me clean that one. x1 cube equals to x2 cube. Once you put them inside, it must be equal. Now let's take the cube root of both sides. So what can we see? When we take the cube root of both sides, then it implies that it's x1 equals x2. So once x1 equals x2, therefore the function is 1 to 1. Therefore f is 1 to 1. Okay, let's look at the other one. If f is 1 to 1, let's see if f is also onto. So now you can see that for any y, let's say for any y here being a member of R, what is happening? You can find an x also a member of R such that f of x here equals y, such that f of x equals y. Indeed, so you can say that x equals to, that is, let's say that is, I can say that x equals to the cube root of y. X equals to the cube root of y. In that instance, x equals to the cube root of y. With that instance, we can say that the function is onto. Once we conclude that the function is onto and then 1 to 1, then we can say that the function f is actually, or the mapping f is actually an invertible. It's having an inverse. Okay, so inverse of 1 to 1 and onto mappings. Now suppose that we have the mapping of x, that is f of x mapped to 3x with domain 1, 2, 3 in the arrow diagram below. What do you get? You can see that the mapping 1 goes to 3 and then 2 goes to 6, 3 goes to 9, that is 3 goes to 9. Good. Now if we take the reverse process, then one can say that 3 goes to 1, that's the reverse, and then 6 goes to 2, and then you can also say that 9 goes to 3. Okay, so here 6 goes to 2. Then what do you see? So you can look at the reverse mapping carefully. The values produced can be written in the rule. Yes, it can be written in the rule as f prime of x, that's f inverse of x, equals x on 3. X on 3. Good. So where the x are members of 3, 6, and 9, any value of the inverse, when you put into this function, you get a reverse. You put 3 inside, get 1. You put 6 inside, get 2. You put 9 inside, get 3. That's the inverse as a reverse, the process of reversing. So in this instance, the inverse of this mapping is f of x prime map to x on 3. Okay. So now we can also visualize the relationship by a graph. So let's see the next section for the graph. Okay, nice. So you can see that the f inverse is that is x on 3. See the graph, and then we can also see the f of x. Look at the graph here. So what can you say about the two relationship between the two graphs? So we can see that the relationship between the two graphs can be seen as reflection in the line y equals to x if done transformation or rigid motion. Reflection in the line y equals to x. So this observation will help us to find the inverse of more complicated mappings. So the inverse is seen as reflection in the line y equals to x. Good. So these are the steps to follow if you want to find the inverse of a mapping. So the first one is you write the given equation as y equals to f of x. That's the first step. Write the given equation as y equals to f of x. And then the next step, you swap the letters x and y. They're the same as reflecting the line y equals x actually. So rearrange the formula into a new y. So here you say make y the subject, and this gives the inverse of the mapping. Let's look at examples. Find the inverse of f of x equals x on 2. So the first step is that you write the given mapping as y equals to f of x. So you can say that let y equals to x all divided by x plus 2. That's the first step. Then the second step says that swap the letter. How do you swap? So we interchange or swap. So we are going to swap, or you can also say interchange the values. So I can say that x equals to y all divided by y plus 2. Wherever I see x, it becomes y. Wherever I see y, becomes x. You swap the values. So after swapping the values, rearrange the formula into a new y equals to f of x. It means that make y the subject. Make y the subject. So we want to make y the subject here. So make y the subject. Alright, so how do you make y the subject? You just do cross multiplication. Go to xy plus 2x equals to y. So you factor, you group like terms, and then you factor your y out. So when you factor your y out, you get y equals to, you factor your y out and you divide through by the sum. So you get y equals to, that is 2x, or divided by 1 minus x. 1 minus x. Good. So this one is what we call the inverse. So f inverse of y of x is actually equals to this y, and that is 2x all divided by 1 minus x. Very, very interesting. Let's look at the next example. So here, before the next example, you should define. So here, all the values of x except 1. So the domain of this function is all values of x except 1. Once you put 1 inside here, what will happen? Think about that. When you put 1 here, it becomes 1 minus 1, 2x all divided by 0. What is happening? Okay, so the function is actually undefined. So we explained that. When do we say the function is undefined? Good. So the next example, find the inverse of the mapping f of x equals x plus 4. So we follow the same procedure. We write the given function as y equals to x plus 4. So you can see that let y equals to x plus 4. So you interchange x and y. So I can get my x equals to y plus 4. So you make your y the subject, and then y equals to x minus 4. Therefore, what will be your f prime? F prime or f inverse of x equals x minus 4. And then what value does it make it define? So all members of R, this domain is that x is such that x is a member of all R. So that will be the domain. So in actual, that is the inverse. Good. So I leave this one to you as an assignment. So you go and do this very well, and I think when you do this, the answer is actually f inverse of x equals, you get square root, clear this, so you get square root of tan inverse of x, tan inverse of x minus 4. Okay, so tan inverse of x minus 4. When you do it very well, so as an assignment, do this as an assignment. Good. So in this session, we look at the condition for mapping to be invertible. We also look at steps to find the inverse of a mapping. Thank you. In the next section, we're looking at the binary operations.